Okay. All right. First, I want to find out any questions or anything we've done so far. We've finished chapter 1. I did have a question this morning about infinite limits. I decided to skip that section so we could move on to chapter 2. Does anyone feel like they need those in their major and their studies? Is that something that's emphasized that you know of? 1.5 covers it, and if you do need anything, see it, but if you want some instruction on it, I'll be glad to go back and do that. I chose not to test you on that because we weren't going to go over it, so if you're okay, we'll move on to chapter 2. Any questions or any requests for that? Okay. So let's go on to chapter 2, differentiation. All right. Section 2.1 is talking about the derivative and the tangent line problem, which is probably, I can't say this for sure, but it's probably one of the initial things that prompted Newton and maybe Leibniz as well, but definitely Newton to pursue this concept of calculus. So what we're going to do, objectives here, are find the slope of the tangent line to a curve at a point. We'll use the limit definition to find the derivative of a function, and we'll understand the relationship between differentiability and continuity. They are related, but they're not quite the same. Okay? All right. Names, please. Go with the names and faces. Catherine. Okay. There you are. And Will. Okay, got it. Wait a minute. Already marked Will here. Say again? Wells. Okay, got it. I can't hear. Jordan, right? Okay. All right. I'm excited to be here too. Okay. All right. So, let's start with the tangent line problem, as if that's a problem. Okay? Calculus grew out of 4 major problems that European mathematicians were working on during the 17th century. Okay? One was, what is the slope of a tangent line? Because to determine a slope, you needed 2 points. But a tangent line only touches a graph at 1 point. So there was a problem. The velocity and acceleration problem, which they could find average velocity, average acceleration, but they couldn't do instantaneous velocity or acceleration, which basically is the same problem. Okay? The minimum and maximum problem. Okay? When do you reach the maximum or minimum of whatever your function is? That's an important thing to know, and you could approximate it, but you never knew for sure. And that also relates back to the tangent line problem. And then finally the area problem, and this was another big motivator, at least for Newton, because remember Kepler's laws of planetary motion, one of them that the area swept by the motion of a planet around its center, which would be the sun or whatever, the area in each time period was the same. How do you determine the area, okay? When it's a variable thing, an elliptical path, that was a very tough issue. But that's the fourth. We're not getting to that yet. Maybe at the end of the term we'll begin to hit that, but that's basically a Cal 2 problem. These 3 we'll hit in here. Each problem involves the notion of a limit, and calculus can be introduced with any of the 4 problems. Okay? We're going to start with the tangent line problem. Okay. What does it mean to say that a line is tangent to a curve at a point? Okay? Seems like that's a pretty obvious question, but let's start with a line that approximates what's going on in a curve. Here's a curve. You pick 2 points on the curve. The line here between those 2 points is called a secant line. Okay? That secant line connects any 2 points on a curve, And that's approximately the rate of change. The slope of that line is approximately the rate of change of that. In fact, it's the average rate of change between this value of x and that value of x, when y is going from here to there. Okay? Essentially, the problem of finding a tangent line at point P boils down to the problem of finding the slope of the tangent line at point P. Okay? You can approximate that slope using the secant line, like I just said, through the point of tangency and a second point on the curve. So if you're interested in the slope at this point here, pick another point fairly close to it. That's going to approximate it, but obviously it's not the same. Okay? Now, this would be a lot harder to do, but to me, this approximates the slope of the tangent line midway between those points much better than it approximates this. But that gets to be a really hairy problem if you start trying to do that. So we'll approximate the tangent line here at C, alpha C, using that secant line. We'll go a little bit more on x, delta x, and that takes us up to a place at alpha of C plus delta x, which is delta y, okay? And then the delta y over delta x, as we learned way back in algebra a long time ago, that is the slope of that secant line. Y is overrun. Change of y over change of x. If C delta alpha C is the point of tangency, and the C plus delta x, that's how far you go on x, and alpha C plus delta x, how much further you go on y from alpha C, is a second point on the graph of F. The slope of the secant line through those 2 points is given by substitution in the slope formula. M is equal to y2 minus y1 over x2 minus x1, where y2 is that one, alpha c plus delta x, minus alpha c, that's the change of y, over the change of x is c plus delta x minus c. Well, now the numerator is sort of messy, but the denominator, sort of simplifies. C minus c goes to 0, so that gives you the slope of the secant line is the change of the y values divided by the change of the x value. Well, of course, that's what we had there, but this is alpha c. We can calculate this, we can calculate that, and we can calculate that. How much did the x change? The right-hand side of that equation is a difference quotient. Did y'all have pre-calculus algebra? You probably did difference quotients. That's why, yes?
In consideration to the test, the first problem talks about find the tangent line to
It's square root of x.
yeah, and it says m equals. Is this the m that you're supposed to equal in this one?
Okay. What problem are you talking about on the home?
The test, it's
on this test, the first test?
yeah.
Okay.
That's why I was a little confused because
Did I give you the right test? No? Okay.
Consider the function f of x equals the
Yeah,
square root of
it
x.
says estimate the slope m of the tangent line there. Okay.
would this help cover it for the test? Like, wouldn't this section build upon so we can actually be able to do the test? Or
Okay. Yeah. It says estimate, okay, consider the function, estimate the slope at there, and what it wants you to do is pick, basically doing the same thing here, okay? But we did it there. They, back then you chose several points and you saw which way it was headed, okay? We're going to do the same thing here, but what this is leading to is a more formal way of doing it. You don't have to go back there and do approximations anymore. So that's what we're heading at. But yeah, that first question is basically asking this. But that was from 1.1. Which back then, and that's the thing, he's repeating a lot of this. He talked, the tangent line problem is on page 49. And you see the same formula that we have here in 2.1, he's doing there. But we're going to move off of just doing limits to come up with something a little bit more precise. But the tangent line problem, they want you to do it the way they did in 1.2, just doing a limit. We're going to start with that, but then we're going to find a lot better way to do it. Okay. Now, was that your question? Yeah. And was it yours too? Okay. Yeah. So we're starting the same way. The same thing was in 1.1. Okay. That's the difference quotient. The denominator delta x is a change in x. The numerator is your change of y. Okay. Just that simple. The change of y over change of x, rise over run. Okay. Now, getting back to this, and same thing we did in 1.1, just repeating it, you can obtain more and more accurate approximations to the slope of the tangent line by choosing points closer and closer to the point of tangency, as shown here. If this is your first delta x and there's your first delta y, okay, then choose a smaller delta x, smaller delta y, and guess what? That line is not a bad line to the tangent. This is even closer, and this is even closer. And then finally, in the limit, you're a tangent line. But you can't do a delta y over delta x when delta x is going to 0. So that's where a limit comes in. Okay? Same thing here. That's big. It's not a tangent line, but fairly close to the slope. Smaller delta x and smaller delta y. That comes closer to being that. Whoa, that's really close there. There's your tangent line. It's the limit as delta x approaches 0. Okay? And that's what we'll be doing. So here's the definition of the tangent line with slope m. And this is, they led you up to this, but didn't quite say it in section 1.1. They just talked about it. This is then the definition. If f is defined on an open interval containing c, okay, c somewhere in that open interval, and if the limit is delta x approaches 0, delta y over delta x, the limit of this is the change of y, alpha c plus delta x minus alpha c, divided by delta x. That is your slope. If that limit exists, then the line passing through c alpha c with a slope m is the tangent line to the slope at the point c alpha c. Okay? The slope of that tangent line to the graph of f at the point at c alpha c is also called the slope of the graph. Okay? You don't always have to say the tangent line. The slope of the graph at that point. Later, when that line represents the velocity, that would be the instantaneous velocity, not average velocity, which the secant line would be. Okay? So here's example 1. All right. To find the slope of the graph, f of x equal 2x minus 3. Really complicated graph, right? What's that a graph of? What kind of function is that? Second?
It's just a linear.
Yes, a linear function. So I think most of us should probably figure out the slope right off the top. But we're going to do it. When c is equal to 2, we find the slope of c is equal to 2. Apply that definition of slope to the tangent line this way. The limit is delta x approaches 0 of f of 2 plus delta x minus f of 2 divided by delta x. Okay? Well, if this is your argument here, okay, then what you do, f of x is wherever you see the x, put this in its place. So that would be 2 times 2 plus delta x minus 3. Okay? So that's this part. Minus 2 times 2 minus 3. So you're just plugging this in for that f and that in for that f, divided by delta x. Okay? Now, pretty easy math to do here. You would think, why in the world would you waste your time doing it? But let's do it. Ooh, let me get my pen back. Okay. So this would be the limit as delta x approaches 0. And what would this be? Multiply that through. 2 times 2? 4. Continue.
What's the delta x? That's 0. So
plus,
0. So 4.
no, 2 times this,
2 times delta x.
2 delta x, perfect, minus 3, minus 4, minus 3, and that's divided by delta x, okay?
So in these situations, we do not plug in 0 for delta x.
No, not yet. No, we don't do that because you can't plug in, you can't divide by 0.
Right.
Okay, so let's continue. Limit is delta x approaches 0. Okay, what would this give you?
12.
Second?
12.
No, you're,
4 times.
no, it's not times. 4 minus 3.
Sorry. 1.
1 plus 2 delta x help me, minus 1 divided by delta x, and what's 1 minus 1? 0, and then delta x over delta x is 1, so you have the limit is 2. Okay, you see it?
Now, I think all of us going to look at that linear function and say, well, the slope is 2. It's 2 everywhere. Not just at c equal 2, but everywhere it is. But you see, we don't ever plug in, well, I mean, you could start that way and say, no, we don't know, well, yeah, we do know. As delta x is approaching 0, this would be approaching alpha 2 minus alpha 2, that's 0, and delta x is 0, 0, 0, indeterminate. So when we proceed to try to manipulate this. So yeah, you might start by trying that, but every time with a derivative, it's going to be 0, yes.
Are you sure it's not just going to be delta x left?
Say that again?
Why didn't you get 2 delta x? Would it not just be 2? Or not, I mean, would it not just be delta x?
Okay.
So you're across the
Right up here.
Yeah.
2 times 2 is 4. 2 times delta x is 2 delta x.
Yeah.
Okay. And then minus 3. 4 minus 3. Okay. So here, 4 minus 3 is 1 plus 2 delta x minus 1 divided by delta x. 1 minus 1 is 0. And then the delta x divide away, and you're left with 2. That's your slope. Okay? Does that make sense?
Yeah.
Okay. All right. Now, we've just seen that the slope of a linear function is its slope. Okay? Is that m. Okay? So that's good to know. Okay? Let's see how they proceed. I bet you it's pretty close to the same thing. 4 plus 2 delta x minus 3 minus 4, and they took out the parentheses early, made this a minus 4, and minus a minus 3 is plus 3. So they sort of snuck that in there on you, but it's legal. And then, at this point, you can look at this and say 4 minus 4 is 0, minus 3 plus 3 is 0, so you now have just the limit of 2 delta x over delta x. And you see, you can't let delta x go to 0, but you can divide it out, can't you? So let's divide it out, and that gives you a limit of 2, which is 2, okay? 2 is the limit of 2. Pretty straightforward. Any questions? All right. Now, it says slope of alpha C, when C is 2, and when we plug that in to 2x minus 3, that would give you alpha C is 1, alpha 2 is 1. So at that point, the slope is 2, is shown here, okay? But of course, that slope is 2 everywhere on the line, not just at 2, at 3, at 1, everywhere the slope is 2, because that's a linear function. But what we saw before, if you let the delta x even be as large as 1, okay, then that would give you a change of y from 1 to 3. So it would be 3 over 1. No, change of y would be 2. 3 minus 1 is 2. 2 over 1 is 2 is the slope. But that's because it's a straight line everywhere. Okay. So the slope at 2, 1 is m is 2. At every place m is 2 because that is indeed a straight line. And the slope is mx plus b. All right, that definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. In that case, all bets are off. For vertical tangent lines, you can use the following definition. If f is continuous at c, and the limit as delta x approaches 0, f c plus delta x minus c, this. If that's one of those, and here's probably we should have done 1.5, is an infinity. In other words, this, as closer you get x's to each other, if you're approaching a vertical line here, you don't have a slope. It's an infinite slope, okay? If that's the case, or going this way, then the vertical line x equals c passes through that, and vertical tangent line is a vertical tangent line with an undefined slope. That's the point. We don't talk about, I don't talk about slopes being infinity or minus infinity. They're undefined because this thing could be bigger, that thing's still 0, it's still, that's an undefined slope. That slope you will never, if that was what you're given 2 points on that line, 7 minus 3 over 0, that's undefined. Not indeterminate, undefined. So that's an undefined slope. Or you can say the slope is infinity. Okay? Now, here's an example of that. Here is a function, and this looks like a lot like what they sometimes call a logistic function. It has a change of, well, I don't want to get into that. We haven't talked about it yet. This is your function. For every point on here, there's one and only one value here, so that is a function. It has a slope here, and here, and here, and here, and there, and there, and there, and there. There's slopes everywhere, except there, okay? There's your tangent line there. It's vertical. It has an undefined slope there. And if you'll notice here, the slopes are gradually increasing, positive, and they're getting very, very, very positive, and here, undefined. And then they start decreasing from that, still positive, and they look to be approaching 0. It looked like they were coming from 0 to here too. So that's the case where you do have a vertical tangent line, the slope is undefined. There is no slope. They can say the slope is infinity, but that's not a number. It's undefined. Okay. All right. Any questions on that? Now, we will be hitting that toward the end of the course when we do have undefined slopes. Okay. When the domain of F is the closed interval A to B, that includes A and B, you can extend the definition of a vertical tangent line, to include the endpoints by considering continuity and the limits at the right, from the right, okay, not at the right, from the right, x equal A, and from the left for x equal B. Okay, and that's what we, again, probably was discussed more in 1.5, but we did it, and what we did as well. Now let's see, there was example 1. Okay. Before we proceed, let's do example 2. Okay, do I have more room there, or there? I think there is better. So let's do example 2 here. Find the slopes of the tangent line to the graph of f of x is equal to x squared plus 1, okay,
at the points 0, 1 and negative 1, 2. Okay? Now they show it in the figure, but being the cynic that I am, I want to make sure these points are indeed on that curve. So how do we do that? How do you know that that point is indeed on that line, on that curve? Plug it in. So you plug in a 0 for x, and what do you get?
0.
Say again?
0 plus 1. 0 plus 1, 1.
Yeah, you get a 1. So 0, 1 is a point. How about negative 1?
2.
That gives you 2. So sure enough, those 2 points are on that. So that's a legitimate question. If that was not posed well and those points were on the line, you're going to have a hard time finding the limits, okay? So this has nothing to do with the wording above there. I was just looking at that saying, what does that matter? Okay, so let's find that. We want to find the slopes of the tangent line. So what is the slope of that tangent line? What's the definition formally?
y2 minus y1.
Okay, it's the limit as delta x approaches 0 of, you started it before, f of x plus delta x minus f of x, all right, over delta x. That's the formal definition, okay? Now let's plug in your x equals 0 here. Not delta x equals 0. So here's going to be m at the point 0, 1, okay? It's going to be the limit as delta x approaches 0 of f of 0 plus delta x, okay, minus f of 0. Got it? Okay, over delta x. Okay, let's plug in what that gives us. Okay, the limit as delta x approaches 0 of, what's f of delta x? If f of x is x squared plus 1, what's f of delta x? F of x says, whatever this is, the x is, you square it and add 1 to it, right? That's what the function tells you to do. So this is now doing that f on delta x. So what will you do? Square delta x, okay? So that would be delta x squared plus 1 minus, and what's f of 0?
0.
Say again?
Not sure. 0.
F of 0. Do the same thing. Plug in a 0 here.
So just 1.
It's 1, okay, minus 1, okay, over delta x, right? Okay. Now, what's 1 minus 1?
0.
Second? 0, okay. So there you have delta x squared over delta x. What does that give you?
Oh, that was the last part.
Just delta x, right? Okay. Now, we don't like having delta x's in the denominators because you can't divide by 0. But once you've divided that out, all you have is the delta x in the numerator. What's the limit as delta x approaches 0 of delta x? Say again? As delta x approaches 0, what's the limit of delta x? What's the limit? As delta x approaches 0, what's its limit? I mean, it sounds crazy. That's the limit of as p approaches 3 of p. What would that be? 3. So this would be 0. So that limit and that slope is 0. Okay? We're going to look at the figure in just a minute and see if that's indeed right. let's do the same thing for this one. Okay? Again, this time we're going to do the slope. You want to do this in a different color? What color you want? Red. Okay? All right. So M at negative 1, 2, okay, will be the limit as delta x approaches 0 of alpha of, does any yeah, things do change here, okay?
Here your x is now a negative 1. So what's the limit of, this would be alpha of negative 1 plus delta x, right? You're doing the second point. Here your x is negative 1. So now you're taking the limit of alpha, forget this one, this is the previous one. We're doing this. Alpha of negative 1 plus delta x, right? Okay,
so you put that in there. Alpha of negative 1 plus delta x minus what? Alpha of negative 1, not negative 1, alpha of negative 1, divided by, denominator is still delta x. Okay, now we've got to calculate. The limit as delta x approaches 0. Now, what is alpha of negative 1 plus delta x? Alpha of x is, take what's in here, square it, and add 1 to it. So you take what's in here, negative 1 plus delta x, right, and square it, right? Negative 1 plus delta x squared plus 1. That's what this tells you to do. Your alpha says do that to whatever's inside of here. Minus, now, you plug in a minus 1 up here. And what does that give you? 2. Okay? Now, that's what we got here too, so that makes you feel warm and fuzzy about it. And this is all over delta x. Okay, now we've got to square negative 1 plus delta x. How do we do that? It would be a 1. What's next?
Delta x squared.
Not yet. Okay?
remember you got a cross term. It's, I don't know if y'all follow these little, this squared plus twice the product of these plus that squared. You got this squared and you did that squared, but you forgot about the one in the middle. If you need to, FOIL it. Okay? That's always legal. It's -1 plus delta x times a -1 plus delta x. That's that thing squared, right? Multiplied by itself. Okay, FOIL it, and you get a,
minus delta x.
okay, you get a 1, and then you get minus delta x, and then you get another minus delta x, and then finally you get a plus delta x squared, which you did say, okay, delta x squared, okay? So this gives you 1 minus 2 delta x, right, plus delta x squared, that's that thing squared, that's that, plus 1, that's that, minus 2, all divided by delta x, okay? Now, can I take off some of my lines to make it a little easier to read? Get these out of the way, okay. Now, what would that be? The limit as delta x approaches 0 of, now what have we got here? Let's see, I can lose that parentheses too because I've never closed it out. Okay, I could have, but no reason not to. Here we have a 1 plus 1 is minus 2. That adds to 0, right? So that gives us
negative 2 delta x.
negative 2 delta x plus delta x squared divided by delta x. Okay? What can we do to that numerator to help simplify? Factor out a delta x. Very good. Okay? So that will be the limit as delta x approaches 0 of delta x factored out, and that left you what? Negative 2 plus delta x. Very good. And you divide that by delta x. Well, guess what delta x over delta x is? 1. So it disappears. Now we're happy campers. Why? Because now we can take that limit. The limit of negative 2 plus delta x, as delta x goes to 0, is what? Delta x goes to 0, what does that become? Negative 2. So there's your limit. Okay, now let's see if they show the picture. I hope they do. Well, I got to erase all this. If they don't show the picture, I'll have to go back and draw it. Okay? Yeah, they don't. Oh, of course not. I was doing the whole thing. Sorry about that. I have to draw the picture. Okay. In fact, well, it's too late now. So let me.
Isn't there an undo button?
Second?
I was about to ask, is there not an undo button like you undo your previous action?
Not when I erased it. Yeah. I can go back a slide, but there's nothing. No, it does. This is a little cheap thing that the school didn't want to pay for a good. I didn't say that, did I? But anyway, here's your graph. Okay, I'll tick off a few points. I knew I didn't need anything below because when I do the function f of x equal x squared plus 1, when x equals 0, what's the f? 1. When x is equal to 1, what's your f? 2. When x is negative 2, what's your f? I mean negative 1, what's your f? When f is negative, when x is negative 1, f of negative 1. Say again? 2, okay. When x is 2, what's f? Say again, 5? 2, 3, 4, 5. Okay. And when it's negative 2, it's 5. And when it's 3, it's 10. That's off scale. So this will be going like this. Okay? A parabola. Elevated by 1, that's your vertical shift upward by 1. Simple, straightforward parabola. And it's saying here at x equals 0, here is the point in question. What's the tangent line there? There it is. Well, I don't draw it too well. It's supposed to be touching only that point. But what's its slope? 0. And that's exactly what we found it was. Over here at negative 1, 2, when you draw that, and we did that in red, so let me go back to red here. Okay. If you drew the tangent line here, I don't draw tangent lines too well. What is its slope? What do we find it? Y'all were writing that, right? No. Okay. But what was that? Where was it there? So m was negative 2. And sure enough, that looks like it's going down 2 for everyone across. So down 2 for it. Look at that. I even intersected the right place. Yep, the slope of that tangent line is negative 2. Slope of that tangent line is 0. It gave it to us by the formula without having to do all those approximations and evaluations and stuff and seeing what it seems like it's going toward, which is what your first test, that first question, is asking for. Plug in values see what it's going toward. Yes?
What's theta x squared divided by theta x?
Say this again. Oh, what's that little triangle? Is that what you said?
What you call it? Yeah, what you call
Delta.
it? What's delta x squared divided by delta x?
Oh, okay. Let me get my pen back. Dark. So delta x squared divided by delta x. Huh? Yeah. That would be delta x squared would be delta x times delta x, right? That's what it means to square it, right? Divided by delta x. Delta x is 1, that would just be delta x. Okay? As delta x is approaching 0, sure enough, that's 0. Right? Okay. Does that answer what you're asking? Yeah. Good deal. Good question. Okay. Now, that stuff about vertical tangent lines follows example 2. I got sort of out of order there. So let's move on to derivative of a function. This is on page 103. Now, the limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, differentiation. Okay? So we came that close to do it. In fact, we did find the derivative. Okay? Now, if we had done it the way the book did, we'd have had it exactly. Okay? Definition of derivative of a function. Derivative of a function of f at some value x is f prime. Now, that's a notation that's sort of grown into the lexicon here. I don't think that either Newton or Leibniz used it, but it's just a real nice shorthand notation. Okay? Newton used an f dot if it's a time derivative, but we're not using the dots. We call that phi spec notation because it's real easy to mistake a dark place on the page for a dot. So this is f prime of x is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. Just like we've seen before. This is a definition of the slope of a tangent line. That's the definition of a derivative. Provided that the limit does exist. Now again, vertical tangent lines, they don't exist. Okay? Discontinuous functions, they don't exist. Okay? So for all x for which that limit exists, f prime is a function of x. If x is in here, x will also be in the derivative. Now, that x may be 0, but it will be in the derivative. Okay, we'll see that in a little bit. Be sure you see that the derivative of a function of x is also a function of x. That new function gives the slope of the tangent line to the graph of f at the point x f of x, provided that the graph has a tangent line at that point. In other words, that it's not a discontinuous function or it doesn't have a vertical tangent. Okay? The derivative can also be used to determine the instantaneous rate of change. So now we're getting into the second part. This is the same as the velocity, simply rate of change as one variable with respect to the other. Doesn't have to be time, but it generally is. Can I get your name, please?
Tiara.
Tiara, got it. Finding you is the other part. There you are. Okay. Good deal. All right, we're on page 103, near the middle of the page. Okay? The process of finding the derivative of a function is called differentiation. A function also is called differentiable at x when its derivative does exist at x and is differentiable on an open interval, a to b, when it's differentiable at every point on that interval. Okay? So, in addition to the prime notation, f prime of x, which is read f prime of x, other notations are used, and this may be a little confusing, hopefully not too bad, for y is equal to f of x. The most common are these. Of course, f prime, that means first derivative of f at x.
The other, which we often call the Leibniz notation, is dy over dx. Now, we're good friends with an Indian family in town, and their oldest son did his undergraduate degree in India, and he was in computer engineering, and when he was doing his calculus, he had some problems when he come home to the States here. I would tutor him in calculus. And for the longest time, I couldn't understand what he was saying. You know, Indians tend to talk a little rapidly, and he called this d by dx. D by dx of y, okay? D by dx of y, okay? D by dx. So I thought, what in the world is he saying? And then finally I figured out what it was. So I get sort of tickled with it. And this is y prime, because y is equal to f of x, so you can say f prime or y prime, okay? Or d by dx of f of x, that's another way to express it. This is d by dx of y, this is d by dx, because f of x is y. Now, here's another one that comes along a little bit later. We won't use it, I don't think, in this course at all, but you'll use it later. The capital D means this operator, the d by dx, okay, with respect to x of the function y. I guess you could put of the function f of x as well, but most of the time it's that. So this d by dx, however you say it, is an operator operating on the function y. The prime means operating on the function f of x. Prime operating on y. This thing operating, this thing right here is this capital D sub x. That's what's in the denominator. That means that operator on this function, either f of x or y, because they're the same thing, that's your derivative. So there's lots of different notations. Use whatever you're most comfortable with. Be familiar with them all. This notation, d by dy dx, is derivative of y with respect to x, or simply dy dx. They'll quite often say it that way, dy dx. I've tried to say dy by dx, but you don't have to say the by there. Using the limit notation, you can then write, and this is where this comes from. dy dx is the limit as delta x approaches 0 of delta y over delta x. Now, it's not a huge stretch to think the Greek delta is becoming the little d in both cases. So this stands for that. This is if it's a finite change. This is if it's incrementally small change, okay? Now, this dy is, the y then would be, and the delta is the difference between f of x plus delta x minus f of x over delta x. Exactly like we had before. And that is this. This is all circular. I mean, you can plug in any of those things on either end and you get the same deal. But that's what this is. It's the limit as the deltas go to 0. Okay? Remember, if this is going to 0 and that's not going to 0, you can't take a derivative of that. That's it. That's an undefined form. Only if that's going to 0 as that's going to 0, then you can call it dy dx. Otherwise, just, limit doesn't exist. All right, so let's do example 3. To find the derivative of f of x equal x cubed plus 2x, use that definition they've gotten right here to do it. So that would be the limit as delta x approaches 0 of, now what is f of x plus delta x? You tell me. F of x plus delta x. If that's what f of x is. I wrote it there so you can plug it in. And what does that give you? X plus delta x cubed. See, this function says take whatever is inside the parentheses, cube it, and then add 2 times it. So this is what's in the parentheses here is x plus delta x. So you take that and cube it. And what next do you do to it?
Plus 2 times, what do you say? X plus delta x. That's exactly what that is.
Now, I know what the square of a binomial is. Anyone know what the cube of a binomial is? You can either square it and then multiply it by itself, or have any of you run into Pascal's triangle? Huh? Heard of it?
It's the one.
Yeah.
Okay. Here's Pascal's triangle. 1, 1, 1. 1's always on the outside, but once you get to an interior, you add these two together. That would be a 2. Then you put 1's on the outside, and then what do you get here? 3. 3, right? And then put 1's on the outside. What would be next? 4.
No, that's
6. 4 and 1. And you can keep on trucking as long as you want to. Okay? This is, let's call it x plus delta x to the 0th power, because what is that? Anything to the 0th power is 1. And this is x plus delta x to the 1st power, because that's x plus delta x, right? Those are the coefficients, right? And when you squared it, what was that? Wasn't that x squared plus 2 x delta x plus 1? Those are your coefficients. So the next one would be, you tell me. You see the pattern? Now, let me tell you the pattern of the exponents. This one has none. I mean, it's just a 0, so that's 1. No exponent. This, the exponents are 1 and 1, right? And this, the exponent is squared, 1, 0, right? Squared. I did that wrong. Sorry about that. I forgot to put my delta x squared. Okay. Okay. You square the first one, and you, whatever the terms are here, they're going downhill here, 2, 1, 0, uphill here, 0, 1, 2. Okay? Does that make sense? The powers, the exponents, if you have two things here, if that was just a plus 1 or something like that, then there would be all 1's at the end. But this has the x squared. Okay? So you tell me what this one would be. I'll start it off with x to what power? Cubed plus what coefficient? 3 times, no, not 2, okay? 3 times x squared delta x to the 1st power. I really don't need the parentheses in there, so let me take it out, okay? Okay, and then the next coefficient is is 3. Now this time you're reducing the x by 1, so that would be x, but you're increasing the delta x by 1, so that would be delta x, whoops, wrong. You gotta be a little careful with your parentheses. Delta x squared. And then finally your last coefficient is 1, and that would be reduce this one, x to the 3, 2, 1, 0, that's just 1, and this one is 0, 1, 2, delta x cubed.
That's what x plus delta x cubed is. Now if you had coefficients in here, you have to include those in, but these are the coefficients of the expanded terms. This is called the binomial theorem. Guess who came up with this? Newton. Okay, he came up with so much of this mess. Stuff. Okay, so that would be x plus delta x cubed would be x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. That's just the first one. Now do the second part. Can I erase Pascal's triangle because I'm running out of room? All right? Okay. Now, there are other ways to do binomial expansion besides doing Pascal's triangle. That, to me, is the easiest way, but there are other ways to do it. But if you're okay with it, we'll not go into those now. Now, let's do this last part, this part. What does that give you? What does that give you? Not that hard, I don't think. 2, it's plus 2x plus 2 delta x, right? Now we got to subtract off our f of x. Well, there's our f of x, so let's just subtract it off. That would be a minus x cubed, right? Okay. Next part. Not that hard. Minus 2x. I'm subtracting off that, right? Okay. Minus 2x, right? There's the numerator. Our denominator is delta x. Okay. Now, big, long, hairy mess here. But what do you notice you can do with that numerator? Simplify it a little bit. Okay, not yet. How about combining like terms? There's an x cubed, there's a minus x cubed. Gone, right? Add to 0. Anything else? A plus 2x and a minus 2x. Gone. Add to 0, right? Now we can factor out. What's common factor in every one of the remaining terms? Delta x. So that gives you the limit as delta x approaches 0 of delta x times, and what's left when you factor out delta x? First term? Second? 3x squared. Okay. Next term? 3x. You only factored out 1, so that leaves you a delta x, right? Plus, factored out 1 delta x, what are you left with? Delta x squared, right? And then finally, plus 2. Okay. There you factored all over delta x, but now what can you do? Yes, divide out the delta x's. Delta x over delta x is 1. So what's the limit of this thing as delta x approaches 0? Well, this delta x approaches 0, that drags the whole term down to 0, doesn't it? Yeah. As delta x squared goes to 0, that really goes to 0, right? And what are you left with? 3x squared plus 2. There's a first derivative of that function right there. Now, do you want me to cheat a little bit? I think you see it. You've had it right. For a polynomial function, to take its derivative, do the exponent times the coefficient. 3 times 1 is 3, drop the coefficient by 1, 3x squared. Coefficient, exponent, 1 times 2 is drop that by 1, it goes to 0. 3x squared plus 2. Later we'll see this is the easy way to judge your derivative. This is technically what you're doing, taking the limit as the delta x goes to 0, that's the slope of the tangent line, that's all that kind of stuff, but that's what it's going to work out for polynomial functions. Nice, really easy. Okay? So there is, by definition, what that is. Let's see how they did it. Okay? Do I need to leave that on there a little bit longer? They're not going to tell you the shortcut yet. Okay? But let's see what they do. They first say that's the limit of, and what's f of x plus delta x? That's f plus delta x cubed plus 2 times x plus delta x, then minus f of x. That. Okay? Then when they do that cube, I don't think they tell you about Pascal's triangle. They just do it. Okay? How many ravens we have up there today? 2? Last week we had 1. He flew into the window once, but now they're trying to get calculus without paying for it. Okay. So here's the other way you can do this if you don't like Pascal's triangle. This has so many rules. It's x cubed, okay, plus then 3 times x drop by 1, 2, increase this by 1, delta x, okay. Divide that by the coefficient here, which is 1, okay. Then, the next term is 2 times 3 is 6, but it's the second term, so divide that by 2, and that gives you a 3 again. Drop this by 1, x, and increase that by 1, x squared. Then 2 times 3 is 6, so this is the third term, so divide by 3. That's not working right, is it? No, this one, the first one. 1 times 3 is 3, divide by 3 is 1. 1, drop this by 1, increase that by 1, and then this is just multiplied through 2x plus 2 delta x minus x cubed minus 3x. Okay. That's the other way you can do it. Like I just showed you, you can sometimes get confused what you're doing with it. But at this point, the x cubed minus x cubed go to 0. The 2x minus 2x goes to 0. And then you have that left, 3x squared delta x plus 3x delta x squared plus x cubed, delta x cubed plus 2 delta x over delta x, and then divide out the delta x, and then, factor it out, then divide it out. That leaves you 3x squared plus 3x delta x plus x delta x squared plus 2. Take the limit of that as delta x goes to 0. Oh, they show you the line. Okay? And as delta x goes to 0, this doesn't have a delta x in it, so that stays 3x squared. This does, and if that goes to 0, that whole term goes to 0. And this has a delta x in it. If that goes to 0, that whole term goes to 0. And this doesn't have a delta x in it, so it stays 2. So that leaves you 3x squared plus 2. Okay? That's by the definition. Now, that was example 3. They're going to skip over examples 4 and 5. Why? Because those are more difficult. Okay? Don't know. So let's back up and do example 4. Okay? Find f prime of x. This is what we're looking for. When f of x is equal to the square root of x. Okay? Then find the slopes of the graph at the points 1, 1 and 4, 2. Before I proceed, I want to make sure they aren't trying to trick me here. When I plug a 1 in for x, what's square root of 1? Square root of 1 is? Not hard. 1. Okay, 1, 1, that makes sense. When I plug a 4 in here, square root of 4 is?
2.
2, yeah. Those 2 points are on the curve, so I'm happier than I was before.
So we use the definition, right? And then it says discuss the behavior of f at 0, 0. So we'll come back and do something there. 0, 0 again is on the curve. That's separate. Okay, not yet. All right, so what's our definition for f prime? The good fun one. The limit as delta x approaches 0 of.
Wouldn't that just be the square root of like x plus delta x?
Okay, so you want to go on and just plug it in? Is that what you're saying? Okay, that would be the square root of x plus delta x. That's f of x plus delta x minus f of x, which would be square root of x over delta x. Everybody see that's what he did? F of x plus delta x, you're just plugging that into the square root, and minus f of x. Okay? Whoa! Can we do that?
There's another way.
How?
You can do the power rule.
Hey, we don't know the power rule yet, do we? Okay? All right. We did do something like this back in chapter 1. How do we do it?
You gotta square the y on the other side. Like when we did it, we square rooted it. Cancel it out. Square rooted it.
Okay. We had a little name for it. I'll give you a hint. These expressions, because of the radicals there, are irrational. So how do we deal with that? Don't know. I know it was a long time ago. It was at least last week sometime like that. We rationalize the numerator. How do we rationalize the numerator? The conjugate. You got it. And what's the conjugate of that numerator? The square root of x plus delta x plus the square root of x. I think that's what you were heading at, but you weren't quite saying. But if you multiply the numerator by that, guess what we got to do? Multiply the denominator by the same thing, x plus delta x plus the square root of x. Okay? What's that? There's a delta x there. I mean, okay, we aren't doing anything with the delta x yet. Yeah, we're just rationalizing the numerator. Okay, now what does that become? The limit as delta x approaches 0 of, and what does that numerator give us? When you multiply the sum times the difference of the same two numbers, what do you get? Y'all did this way back in algebra. When you multiply the sum times the difference of the same two numbers. In other words, a number by its conjugate. What's the answer? A minus b times a plus b. Oh, that was back in algebra. You don't need to remember that anymore, do you? What was that? A minus b times a plus b. For it if you need to. A times A is? A squared.
These cancel out and it leaves with B's.
Yeah, these two cancel out and then you get a minus B squared. Yes, you remember that, didn't you? Okay. So what would that be in this case? These two multiplied together, they're the same thing. What does that give you? X plus delta x. The square roots go away, right? When you square a square root, you lose it. Minus x. Excellent, okay? Over delta x times, let's leave this alone, square root of x plus delta x plus the square root of x, okay? Now, what happens to that numerator?
the x is canceled out.
Not yet.
Yeah.
The x minus x adds a 0. Now you can divide out the delta x. Don't get carts before horses, right? And that leaves you with the limit as delta x approaches 0 of numerator, it's just a 1, right? Over the square root of x plus delta x plus the square root of x. And someone tell me what that limit is as delta x approaches 0.
What does this become as delta x goes to 0? Square root of x, doesn't it? As that goes to 0, that goes to square root of x, right? Delta x goes to 0, this is approaching the square root of x, right? Plus the square root of x would be square root of x plus square root of x would be how many square? Yeah, 2 square root of x's, okay?
So this would be approaching 1 over 2 root x. Okay? You have just found the first derivative of the square root of x. Okay? Now, that was the first part. Okay? The second part says find the first derivative, the slopes of the graph at these 2 points. Okay? But guess what the slope of the graph is? This is your m. This is it. So let's do the m at 1, 1. So what would that be? Anybody? Help me, help me. Leave me hanging here. Say again? Okay. What does this first one stand for? Ordered pair. X, Y. Okay, now can you tell me what m of 1, 1, if that is 1 over square root of x, 2 square root of x? 1 over 2, because the square root of 1 is 1. Okay? Now let's give me m at 4, 2. What would that be? 1 over 4. Perfect. Now let's investigate what's happening at 0, 0. What would that be?
It's undefined.
Undefined. Absolutely. Why?
It's when you put 0 in the...
Yeah, you get an undefined form, 1 over 0. But why? Let's take a look at that graph. Okay? The square root of x looks something like this. 0, 0, 1, 1, 4, 2. It's that, right?
It's half of an upside down parabola. Okay? The slope here is 1/2. The slope here is 1/4. It's barely going up at all. But what's the slope here? Vertical line undefined. Because guess what? If that parabola was like this, that'd be a slope of 0. When you turn it on its edge, it's a slope. Undefined. Vertical line. No slope defined. That's why you can't do the slope at 0. It's undefined. The function's defined there, but the slope, the derivative is not. Okay. Your picture in the book shows it a little bit better. Can I erase this? Because there is no backup from the book. They don't do this one. Okay. Let's go to example 5. Okay. Would y'all be in favor if I said let's take a bladder break? Okay, all right. Let's do that. Okay. All right, ready for example 5? Now, example 5, even though they didn't show it on the slide set, if you'll notice right under it, it says see larsoncalculus.com for an interactive version of this type of example. So this one, if you don't
like what I'm doing here, go, or even if you do like it and want more amplification, go to larsoncalculus.com and you'll see him describe it better or more fully. It says find the derivative with respect to t of the function y is equal to 2 over t. So I'm going to call this y, that's what they call it, y is equal to 2 over t. And what we're going to do here is looking for the derivative. So I'm going to call that derivative dy dt. You're so used to thinking of y prime as being dy dx, I'm going to actually explicitly say dy dt. Okay? Now what's the definition of a derivative? Same as before. Limit as,
Delta x.
only this time it's t, delta t approaches 0. See that dt is going to back up and be a delta t. Okay, of
Would it be 2 divided?
say that again.
2 divided by t plus delta x?
Delta t, okay.
Delta x.
Okay. You see what he did was, this is your alpha t, so you put alpha 2 plus, t plus delta t. So it'd be 2 over t plus delta t. Exactly. Minus, oops, I shouldn't have said that. What's the next part? That's f of t plus delta t, or y of t plus delta t, whatever you want to call it. What's the second part of the numerator? Second part of the numerator? Minus
2 divided by t.
2 over t, your f of t. F of t plus delta t minus f of t divided by delta t. Got it. Okay. What are we going to do with that numerator? Oh, I didn't show you the shortcut on 4, did I? Your power rule. We'll have to wait on that. I'll try to remember to do it after this one. Okay? What are you going to do to that numerator? What is that a difference of?
You're gonna have to multiply by the.
Say that again.
You're gonna have to.
Say it.
Common denominator?
Ah, yes, these are fractional forms. Whenever you do fractional forms, you got to have a common denominator. What would be your common denominator?
It would be t plus delta t.
Yeah, not just that. T times t plus delta t. This would be 1 over 9, or 2 over 9 minus 2 over 2, you know. There's nothing in common, so the common denominator would be 18, right? Because 2 won't go into 9. Well, t won't go into t plus delta t, so it's the product, t times t plus delta t. You don't buy it, do you? Okay, if this were 2 over 9 plus, or minus 2 over 2, not, that won't work. 2 over 4, no, yuck, why did I choose such a lousy one? Let me erase that. Yeah, get out of there. Okay. All right, let me think. Ah, got it. 2 over 11 minus 2 over 2. 2 over 3. Let's change that to a 3. All right, that would work. All right. 2 over 11 minus 2 over 3. What's the least common denominator? 33. How'd you get it? Multiply them together. Because there's no common factors between the two. So this one, we multiply together. Okay? So your least common denominator is going to be t times t plus delta t, right? So what are we going to do with that? We're going to multiply that by the numerator, t plus delta t over t plus delta t. I forgot my t's in front. Okay, and this one we're going to multiply by t times t plus delta t. Now you probably don't think of doing this, but that's exactly what you do. What you'd have to do up there was multiply numerator and denominator by 33 over 33. Yeah, that's what you would do. Now, what that does for you here, it wipes. Is that really what I want to do? Yeah. Okay. This wipes out that, and this wipes out that. Okay. And this leaves us with the limit as delta t approaches 0 of 2t over t times t plus delta t minus 2 times t plus delta t over t times t plus delta t. Okay? Ugly but true over delta t. Okay. Now, now that we got same denominators, we can combine numerators. That's the limit as delta t approaches 0 of, what does that new numerator become? Two t minus, second, well, it's 2t, let's put them over the same denominator. We got common denominator, so it'd be 2t minus 2t minus 2 delta t. Would you buy that? Okay. Over t times t plus delta t over delta t. Buy that one? Not buy it?
Why is the last one over delta t?
Okay. Second?
Is the bottom denominator?
Yeah. This hasn't changed at all. Yeah. That's been all the way
we have
through.
fractions upon fractions. That's one of the confused. What's going on?
Yeah. Okay. What you've done with the numerator is get it over common denominators. So you got it over common denominator here. What can you do to that numerator?
Cancel out 2t.
Yeah, 2t minus 2t is 0. And then what can you do? The delta t's can go out, right? So what does that leave you with? Okay, that's the limit as delta t approaches 0 of a minus 2 over t times t plus delta t. Okay? Now, can we take a limit there? As delta t goes to 0, what does that leave you with?
Minus 2t.
T times t is? T squared. So your answer is, let me put it up here, minus 2 over t squared. Okay? There is your derivative. Okay. Now you want me to go back and do, huh? The power way? Yeah, I shouldn't be doing this. This is taking all the fun out of the next class or two. But y'all don't mind? Okay. That first one, the example 4, well, what is the limit of f of x, what was the derivative of f of x equal the square root of x? F of x equals the square root of x. Well, first thing I do always
when I have this, I'm taking a derivative, is get it in power notation rather than radical notation. Well, this power notation would be x to the what power? To the what? Say again? You missed. Not second. That'd be x squared. Close, but no cigars. It's to the 1/2 power. All right? When you have a radical, the denominator of your exponent is always the index of the radical. Since this is a square root, you don't see an index, but you understand that to be a 2. The numerator of your exponent is the power inside, so that's just 1. So that's actually 1/2. And then using the little rule we did before, f prime of x would then be exponent times coefficient, 1/2 x to the, yes, you subtract, it would be 1/2 minus 1. And that would be 1/2 x to the minus 1/2, right? Well, minus 1/2 would be 1 over 2 times the square root of x. And that's what we got before.
The way we learned high school was for the formula for it's like n times x to the n minus 1.
Yes, exactly. And that's exactly what we did. But you had to multiply with whatever was here. So n times that. And the coefficient was 1, so it's n 1/2 times x to the n minus 1, which is exactly what this did. That would be x to the minus 2, which this is 1 over square root of x, 1 over x to 1/2. And that's what we got before. Now let's do this one, okay? Your function here, there it is, okay? What would be, we'll go this way with it. This is the same as, and again, first thing I do is get it in exponential notation rather than fractional notation. And what is y is equal to 2 over t? That would be what? What's the exponent of t if you moved it upstairs? Okay, that would be, it would be 2t to the minus 1. 1 over t is t to the minus 1, right? Got it? Remember that? Now take the derivative of it, y dy dt, and that would be negative 1 times 2 is negative 2. T to the, drop that by 1, that would be negative 1 minus 1 is? Negative 1 minus 1 is negative 2. So this would be negative 2 over t squared, which is exactly what we got. You wanted it, right? You wanted to do it this way, right? Yeah. Okay. But you see your limit give you the right answer. Okay? Or your power rule gives you the right answer. You haven't even had the power rule yet. What are we doing that for? Okay. All right. Anyway, negative 2 over t squared. That was their answer. All right. Let's move on to, can I erase this now? Oh, y'all need it a little longer? What, the limit part or my mess at the end? Don't worry about my mess at the end. What's this again? This one? Okay. I rewrote this. You got this part okay? Okay. So, and then to take a derivative of it, dy dt is, well, the exponent times the coefficient. That would be a minus 2 times t to the, subtract 1 from this exponent. Well, minus 1 is minus 2. Well, now to write that in fractional notation would be minus 2, move the variable downstairs and lose the minus sign. That would be t squared. That's exactly what we want to see. T to the minus 2 is 1 over t squared. Make sense? All right. Good deal. Okay, I'll erase now, or someone still need a little bit longer? Okay. So let's move on to differentiability and continuity. Okay. The alternative limit form for a derivative is useful in investigating the relationship between differentiability and continuity. And this is what they call the alternative limit form. I don't know if you remember this from before. They didn't focus on it that much, but the derivative of f at c, the other way to say this is the limit as x approaches c of f of x minus f of c over x minus c. Okay? Now, what that's saying is this x is something off of where c is. C is somewhere here, f is off of that. So this is your y2 minus y1 over x2 minus x1. I mean, that's the same thing, but now x is approaching c, getting closer and closer together, rather than delta x approaching 0. So here's the illustration of that. We want to know the derivative at c of this curve up here. Well, here's f of c up here. Right, there's f of c, that's the y value. Here's c, the x value. And you're moving over someplace x here. Now, it could be back here, but we're going to take it to the right. So x is over here. Here's your f of x up here. Okay? So your slope is the rise over run at f of x minus f of c. That's your rise, the delta y. And your run is x minus c. Okay? So that limit is the same as with delta x's in there. Okay? Provided that this limit exists, and on this curve, yes, it does. Okay? Now, I like the looks of this better because I don't have to keep writing the delta x's or delta whatevers, and my deltas get uglier and uglier the more I write them, if you haven't noticed yet. So this is a little bit easier to write, but maybe not quite. Well, we'll see. Okay. Now, where are they going with this? Note that the existence of the limit in this alternate form requires that the one-sided limits, that as x approaches c from the left-hand side and x approaches c from the right-hand side, must be the same thing. Okay? So the limit, this would be f of x minus c over x minus c, and f of x, that would be c approaches, x approaches c to the right. That those must exist and be equal. Those one-sided limits are called derivatives from the left and the right, respectively. Okay? It follows that if f is differentiable on the closed interval a to b, goodness gracious, how many prepositions in a row here? If it is differentiable on AB, and when the derivative from the right at A and the left at B both exist. In other words, this derivative is differentiable here, and if the same derivative gives you this value you would expect to x equal a from the left, or x equal b, x equal a from the right, x equal b from the left, both of those exist, then it's differentiable on the closed interval as well, as those both exist. Okay, when the function is not continuous at x equals c, it is also not differentiable at x equals c. Okay? For instance, this greatest interval integer function, they love this function, f of x equals greatest integer in x, is not continuous at all of your integers. Okay? Not at 0, not at 1, not at 2, not at 3. Everywhere in between is continuous, and it's differentiable in between, but it's not differentiable at the integers because the function not even defined. I mean, it's defined there, but the limit of the function is not the same coming from the left as the right. Okay? So it's not differentiable at x equals 0, or x equals 1, or x equals -1, or
any integer because it's not continuous there. Okay? So, bottom line here, if a function isn't continuous at a point, you can't take a derivative of that point. Does that mean if it's continuous you can take a derivative? Not necessarily. Okay? You can verify this by observing that the limit as x approaches 0 from the left of this, okay, 0 from the left, this would be the greatest integer in x, okay, from the left-hand side, this would be, on the left-hand side it would be 0, from the right-hand side it would be 1. So this would turn out being a 1, that would turn out being a 0. Can't do it, okay? But if you did it from the other side, this is from the positive side, the limit of this is 1, and this is 1, okay? Would be approaching 1. So that, I'm sorry, 0 over 1, which would, of course, be 0. Okay. Although it is true that differentiability implies continuity, the converse is not true. That's what I just said. That is, it is possible for a function to be continuous at a point, but not be differentiable at a point. And I think that would make sense to you if you picture what's happening there. The classic example is a absolute value function. Okay, they shifted this to the right too, but it's still absolute value function. Absolute value of this. What's the slope of this line as x? This is a negative 1. What's the slope of this line?
1.
A 1. And the slopes at 2,
0.
not defined.
It's
It's one thing coming from one way, the other coming the other way, not defined. Continuous function there, no problem there, but it's not differentiable there. Differentiable here and here, but not there because the limit here, limit there are different. Okay? So, if a function is not continuous, it's not differentiable at that given point. If it is continuous, it's not necessarily differentiable. Here's the key. Okay? They not just have to be continuous, they have to be smooth and continuous. And guess what? That's not smooth. That's jagged. Smooth, like a sine function or a parabola or a cubic function, anything there, smooth, they're differentiable. And continuous. Must be smooth and continuous. And guess what? Polynomial functions are always smooth and continuous. Sine and cosine functions are always smooth and continuous. Rational functions, not necessarily always continuous, but generally smooth, where they're not discontinuous. The other trig functions, secant, cosecant, tangent, and cotangent, not always continuous, so you can't differentiate there, but where they're not discontinuous, they're smooth. Okay? And you can take them in between the discontinuities. All right. The one-sided limit, this is what we just said. As you approach 2 from the left, that limit is -1. As you approach 2 from the right, it's a positive 1, not equal, and will never be equal no matter how close to 2 you get. Okay. So f is not differentiable at x equal 2. The graph does not have a tangent line at the point x equal to 0. Continuous there, but no tangent line. A function that is not differentiable at a point at which the graph has a sharp turn or a vertical tangent line. Okay? So differentiability implies continuity, but the reverse is not true. Okay? And just that smoothness doesn't always count. Because if you have a vertical tangent line, that's smooth there, but it's not differentiable where that derivative doesn't exist. Okay? The relationship between continuity and differentiability summarized below. If a function is differentiable at x equals c, then it has to be continuous at x equals c So differentiability implies continuity. It is possible for a function to be continuous at x equals c, not be differentiable at x equals c, so continuity does not imply differentiability. And I started to say smoothness would, but not then if you have a vertical tangent anywhere. Okay. Whoa! That was it. They skipped example 6 and 7. So let's jump back. Goodness, where are we going to find? Okay, let's clear this out of the way and try to do example 6 and 7. Okay. And number 6 is also found at clarsoncalculus.com for an interactive version of this type of example. Maybe not exactly this one. That's the one we just did, isn't it? How in the world did I miss that? Yeah, there was example 6. We did that. We talked through it. We didn't. And we talked at great length through it. Okay? But, okay. So that was example 6. We did do that. All right, so let's do example 7. And that's the other one I was talking about, but we didn't actually do. The function f of x is equal to x to the 1/3 power. How's another way we could write that function? This is an exponential notation. The cube root of x. That's the same as the cube root of x. Okay, notice here, if you wrote it in exponential notation, the numerator is the exponent of the radicand, that's a 1, and the denominator is the index of the radicand, 3. Okay, so that's what that is. Boy, do they ever, well, let's try doing it by their way. Let's do the limit. Okay, this function is continuous everywhere, okay? The square root of a negative number, the cube root of a negative number is negative, the cube root of 0 is 0, and the cube root of a positive number is positive. So this is continuous everywhere, everywhere. It's actually smooth everywhere, too. The problem comes at x equals 0, okay? And let's see, and they want to use this notation. So x equals 0, 0 is your c. So now we've got the limit as x approaches 0 of alpha of x minus alpha of 0 over x minus 0. Okay? Now, remember our good old test when we were just doing limits and not talking about derivatives at all. We would look at this and say, plug it in, okay? Alpha 0 would be alpha 0, 0, right? Okay? Minus 0, that's a 0 over 0 minus 0, indeterminate. But remember we said indeterminate doesn't always mean you have a limit. You have to determine. If this was 7 over 0, never happened. And 0 over 7, that's 0. Okay? But 0 over 0, it's not that you have a limit, it's you can't tell if you have a limit. So this is an indeterminate form. Let's see what happens if you do that. Okay? Well, this would be the limit as x approaches 0 of the cube root of x. That's what f of x is. I guess I'll do it this way. You can do x to the 1/3. Let's keep it x to the 1/3. Why not? Since that's what they gave it to us as. Okay. I bet you'll see it better if I use the other one, though. So I'm going to leave it cube root of x. Okay, we'll see. Okay. Minus, what's the cube root of 0?
0. Okay, so that's that over x. Okay. Let me erase that. Okay. Now, certainly that limit doesn't exist. I mean, it's indeterminate. Okay. Now, what was our procedure when we had radicals?
Conjugate.
Second?
Multiply by the conjugate.
Okay, and that is if it was a binomial, right? This isn't binomial. We just need to rationalize the numerator. And how do we rationalize the numerator here?
Second? Multiply by the cube root of x squared. Now, maybe you would have seen it just as well or better if I'd have said multiply by x to the 1/3 times x to the 2/3. Would you have seen that just as easily without the radicals? What you think? Yay or nay? I'll go back and do it the other way too. Okay, what does this give you as the numerator?
X.
Okay, x over x times the cube root of x squared, right? Now, there's your x's disappear, and that gives you the limit as x approaches 0 of 1 over the cube root of x squared. And what's that?
Undefined, not indeterminate, strictly undefined. Okay, so that limit does not exist. Okay, you could have done the same thing if you had done it in exponential notation. The limit as x approaches 0 of x to the 1/3. Second? Right. We'll do that in just a second. Okay? Over x. Okay? And multiply this by x to the 2/3 over x to the 2/3. Same thing. You know, this would be x over x times x to the 2/3. I mean, they're just the same forms. 1 over x to the 2/3. And let that go to 0. Not going to happen. Okay. Now, you wanted to do that with the power rule. So your f prime, well, your f prime is this thing right here that we were saying, 1 over this. But let's do the power rule. Okay, that'd be 1/3 times x, which is, 1/3 times 1 is 1/3, x to the minus 2/3, right? 1/3 minus 1 would be negative 2/3, right? Maybe I should have put that stuff in there. I tend to jump. I shouldn't. Okay, that would be 1/3 minus 1. That would be 1/3 x to the minus 2/3, which would be 1 over 3 x to the 2/3, which would be the cube root of x squared. So you see, yeah, that's your answer, but x equals 0, undefined. Definitely undefined. Okay. Even though this is a smooth continuous function, because it has a vertical tangent line at x equals 0, it's not going to be differentiable everywhere. Okay. So,
Wait, what is that 3? You have that 1 over 3 x to the 2/3, but then on the other one, it's just 1 over x squared, run to the 3. And you see on the bottom one you have 1, and that's the same thing, but there's just a 3 in front of that x on the bottom.
Right, okay. Okay, getting from here to here?
No. Look right at the farthest right on 1. Yeah, okay, then look at the one above it.
Right.
You have that 3 in front of that x to the 2/3, which is the same thing as that denominator.
Oh, right. Okay, sorry, wait. Let's see what you're saying now. I think I lost it somewhere.
You're saying why is there 3 in front of the x? As
Yeah.
opposed to in the other situation, there's no 3.
Yeah, hold on. What did happen to it? Okay, f of x is that Yeah, absolutely right. What did I do wrong with this? F of x is okay. Beats me. I mean, I know it's there. I just can't see where I lost it.
Can you start back at the beginning and walk through it?
Yeah, well, let's, I think that, yeah. Okay, this is limit as x approaches 0, f of x minus f of 0 over x minus 0. Okay? And that would be, and then that would be, this would be the cube root of x minus the cube root of 0. There's just no reason to write that down. Over x minus 0, which is x. So that's that, okay? And then we multiply numerator and denominator by it's not the conjugate, this is just what makes that we rationalize it. Multiply this by the cube root of x squared over the cube root of x squared, okay? This gives us x. That gives us x times the cube root of x squared.
Why is the square root under 1 of them, but not
Okay.
under the other x? Yeah. Okay.
I mean,
2 anyway. There's 2 under this one, but not 2 under this one.
what's that?
There's 2 under this one, but not under this
Right, I know. Oh, well, no, I mean, what we're doing is getting this to go to an x. And this times this would be x cubed, cube root of x cubed would be x. That was on purpose, okay?
So you raise x to the second power to get rid of that radical.
Okay. I mean, I look at the book and they get the same thing, and that's really puzzling to me. Oh wait, no, I got the wrong one. Okay. I hate to say it this way, but it beats me. I don't see where the
one's correct. Where the 1
Yeah.
over 3, that's correct. The
Well,
top one-
Are we sure
Well,
about
but the
it?
thing is, this is doing, if we had x equals c, x approaching c, not 0. See, 0 is not defined, and that's all this shows. If we were approaching x equals c where c is not 0, then that would be a different story, okay? And let's do that, okay? Change all these zeros to, okay. And you start over from there. I think that this will give it to us, I think, okay? Because that's a derivative everywhere that's not equal to 0. The one we just did was where it is equal to 0. So if we put as x is approaching c, then that would be that, okay? So this would be x to the 1/3 minus c to the 1/3 over x minus c. Now this time we do multiply by the conjugate. And that would be x to the 1/3 no, it's it's to the 2/3 minus c to the 2/3. I think. I'm going to have to scratch my head on this one a little bit because I'm not used to doing conjugates with other things other than squares. So let's see if this works. And that's a plus. I'm not sure this is going to work. Let's see what happens. I know that those two multiply to be x, and this would be a minus x to the 1/3. No, this isn't going to work.
Can you try to explain to me why you were raising it to another power? Because I'm not understanding why you were trying to do it that way.
Well, let's try it the other way, okay? I'm afraid it won't work either, but let's give it a shot. Make those 1/3, okay?
I was just trying to figure out your rationale. I don't understand.
Okay, let's see what happens there. Obviously, this will give you, yeah, this will work. Sorry, I should have done this to begin with. This will be x to the 2/3, and when you do these two, they cancel out, minus c to the 2/3 over x minus c times x to the 1/3 plus c to the 1/3. See, this is what I was trying to avoid before. Okay.
That's when we usually find like terms that cancel out. But
It's nasty.
you can
It's
cancel-
doable, but it's not a very pretty picture at all. I still don't see how it gets us where we want to go anyway. I don't think that does it either. But you would have to carry that through, and there is no, there's a lot more involved. I think what you have to do, now that I think about it, is multiply by the thing that gives you, now that I think about it. Let me see if this works. And you'll say, why in the world would you do this? But you did ask the question, so you're going to get at least another iteration. If this answer doesn't work, I'm going to hang it up. But I think this will work. Okay, I want to multiply by something that makes this a difference of two perfect cubes. Okay, so I want this to be x minus c.
So it was the same thing we were talking about when we were trying to find the product.
Okay, here's what this will be. If you do x to the 2/3 plus c to the 1/3 x to the 1/3 plus c to the 2/3.
Let's try this and see if it works. This will give you x, right? This will give you a plus c to the 1/3 x to the 2/3. Okay, when you multiply these two together, you'll get these two together. Yeah, these two together, you get a minus c to the 1/3 x to the 1/3. Right. Let's hang it up. That was the one we did before, was to see what happens as x approaches 0. It's not going to give you an answer. That wasn't the same as getting a derivative. Getting a derivative and no wonder they didn't ask you to do that. This stinks. I mean, it's really nasty. I'm sure there's a pretty simple thing I'm overlooking, but it's going to take way too much. It's already taken more class time than it should. We have finished 2.1. All they were asking for was proving that the derivative was undefined there. We did that. I showed you how to take the derivative, but that was irrelated to the fact it's undefined there. So sorry about that. Should have just cut it right there. But that's an excellent question. I'm glad you picked up on that. Sort of. Okay, so let's do homework exercise number 5. And remember, calcchat.com has the odd number solutions, worked out solutions to the odd number problems and tutorial help. So number 5, number 7, any of the odds 9 through 13. 11 is also at calcview.com, so you can see even more detail there. Then do any of the odds 15 to 27, 17's, and they're all at CalcChat, 17's at CalcView. Do any of the odds 29 to 35, they're all at CalcChat, 31's at CalcView. Do any of the odds 37 to 41, they're all at CalcChat, 37's at CalcView. Do any of the odds 43 to 47, they're all at CalcChat, not at CalcView. You can look at or think through 49 and or 51. You can take a look at those. 53. Then do either 55 or 57. They're both at CalcChat. 57's at CalcView. Do 59. And these get a little more esoteric, so if they get you bogged down, don't get too worked up about it. Check it out at CalcChat. See what they've got. If they're not at CalcChat, sort of forget about it. Try to do 61 and try to do 63. Now, they say 63 and 65 you require graphing calculators. So I would say do either or both of those, 63 or 65. Try to do 67. Then do any of the odds 69 to 75. They're all at CalcChat. 69's at CalcView. Do either 77 or 79. They're both at CalcChat. Only 77's at CalcView. Do either 81 or 83. They're both at CalcChat. Either 85 or 87. They're both at CalcChat. 87's at CalcView. Do 89. That's at CalcChat. Try to do 91, or at least think through it. Okay, they say the B part you'll need a graphing calculator. Then there's a true-false 93 or 95, or both. And then 97 is the differentiability and continuity problem. All right, and again, those higher numbers, if they give you really big headaches, don't get a big headache. You know, just move on. All right, let's move on then. Let's move on to. What's that?
What were you trying to get earlier?
No, that was example 3. I went back to example 3 to get room to write. Okay. All right. Now, moving on to 3. And notice here, well, no, this, I was thinking chapter 2 had way extra sections. It's chapter 3 has 9 sections. Don't think we're going to be able to do all of those. Chapter 2 will do most of these. All right, we'll go from current slide. And continuing differentiation. Now we're going to look at the basic differentiation rules and rates of change. Okay? Well, first, find the derivative of a function using a constant rule. Then find the derivative of a function using the power rule, which y'all already know now, don't you? Find the derivative of a function using the constant multiple rule. Okay? And we'll find the derivative of a function using the sum and difference rules. Are we going to get to? Yes. Find the derivatives of sine and cosine function, and then finally using derivatives to find rates of change. So let's do the constant rule. In this section, we'll be introducing several differentiation rules, in quotes, that allow you to find the derivatives without the direct use of limit definition. I know that's sad, but get over it, okay? That we may be through with limits for a while, okay? So see if you can manage it. Here's the constant rule. The derivative of a constant function, if f of x is equal to 17, everywhere at 17, x equals 43 at 17, when it's negative 5 at 17, when it's 0 at 17, any rule is 17. Well, guess what that graph says? A horizontal line. It's always a constant, so that it never changes, okay? No matter what your x is, it's still that constant. The derivative of a constant function, guess what the slope of a horizontal line is? What's the slope? 0. It's not positive, it's not negative. It's not going up, it's not going down, it's 0. That is, if c is a real number, then the derivative, d by dx of c, is 0. Always. The slope of a horizontal line is 0. The constant function has a horizontal slope, is a horizontal, the graph of that is a horizontal line. Notice that the constant rule is equivalent to saying that the slope of a horizontal line is 0, which is exactly true. That demonstrates the relationship between slope and derivative. Okay, so if y is equal to 7, what's dy dx? 0. dy dt? 0. It doesn't matter what your independent variable is. It doesn't depend on anything, so it's 0. They use dy dx. Okay? Now, if f of x is equal to 0, what's its slope, derivative? 0, of course, okay? Because y is equal to 0, that would be the x-axis. And the slope of the x-axis is, of course, 0. Okay? All right. S of t is negative 3. What is the s prime of t?
0.
0, because at negative 3, it would be down here, and always negative 3. That slope is 0 as well. Okay? These are hard, aren't we? We're going to have a lot of these on the test. Okay. How about this one? Y is equal to k pi squared, where k is a constant.
2 pi.
Second?
Is it 2 pi?
Okay. How about 2k pi times pi to the okay. Thing is, that's not a variable. Pi is a number. Oh yeah, 3.14 blah blah. So pi squared is a number. K is a number. So the derivative of a constant, that would be whatever k was times something around 9.43 or 4, something like that. That times that is still just a number. dy dx is equal to 0. That is just a number. Anytime y is a number, its derivative is 0. All right. That was example 1. Okay. They have a conjecture at the bottom. I don't know if it's worthwhile to do or not, because we're going to do it in the power rule in just a minute. What do you think? Worthwhile or not? Oh, just go right straight to the power rule. That sounds like a winner to me. Okay. Now,
it says before proving the next rule, it's important to review a procedure for expanding a binomial, which is what we've done before. Remember the Pascal's triangle? X plus delta x squared, coefficients 1, 2, 1, and here the x's count down, the delta x's increase in power. To the third power, 1, 3, 3, 1, okay? X is decreasing in power, delta x is increasing in power. To the fourth, we didn't do this, so I showed it on the Pascal triangle. It would be 1, 4, 6, 4, 1. Remember, we did do that one. And that would be the x is decreasing in power, the delta x is increasing in power. To the fifth, we didn't do that, but all you have to do is add these two together, get 5, 10, 10, 5, and 1. Okay? So there we have it. Same thing as before. Okay? So the general binomial expansion for a positive integer is, now this is a general. Remember, you start with x to the n, okay? And then you do n, and this is how I did it the second time. Remember, 5 times 1 would be 5, that would be n. X to the n minus 1, it drops by 1, delta x to the first power. Then you do the 4 times 5 is 20 divided by 2, that's because it's the second term. And then that would be, while they didn't have it down here, x to the n minus 2, delta x to the positive 2. And you keep going down. The next would be this times this, but divided by 3. And the x would be n minus 3, this would be x cubed. So your delta x's are going up, delta x cubed. Delta x going up, the x is going down. But delta x squared is in every one of these terms. Delta x is in all these, delta x squared is in all those terms. That binomial expansion is used in proving a special case of the power rule. Okay? And this is really, frankly, to me, a lot of blah, blah, blah. I can do it, prove it, and do every step, and then later I say, why? I mean, but yeah, it's all true and doable. But the rest. So here's the power rule. If n is a rational number, then f, okay, if n is a rational number. Now what do we mean by rational number?
Any of that is an fraction or
Yeah, okay, yes, it can be an integer, it could be a fraction, rational numbers usually mean fraction, and what's more, n could even be negative, okay? It's not irrational though. It can't be the square root of 7, or something like that. Then, if f of x is equal to x to the nth power, that is both differentiable and the derivative is n times x to the n minus 1. You just take the exponent times the coefficient, which you don't see a coefficient here, and drop the n by 1. For f to be differentiable at x equals 0, n must be a number such that x to the n minus 1 is defined on the interval containing 0. In other words, it can't be you can't have a 1 over 0, okay? So if this came up to be a minus 1 or a minus 2 or anything else like that, the x can't be 0, okay? And we'll see examples of that, I think, in time. Not too much time because we're running out of it, right? Okay. When using the power rule, the case for which n equal 1 is best thought of as a separate differentiation rule, and that's just that the power rule when n is equal to 1, derivative of x is 1. Okay? In fact, if you write that, dx over dx, what does that look like? 1. Okay, it looks like the same thing over itself. So sure enough, that is 1. The rule is consistent with the fact that the slope of a line, if the slope of that line is 1, y is equal to x, derivative of y with respect to x has to be 1, just like we did before. Okay? So that makes sense. Okay? Do we have time?
Sure.
Okay, let's do this one. What would that be? What would L prime be?
Yes. I can see it.
Say again?
3x.
Not 3x.
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 3x squared.
Squared, you have to drop that by 1. Okay, 3x squared. Perfect. Okay? What would that one be? And again, what's my little rule? Never do it in radical form. Write it in
Power notation.
power notation. What would that be in power notation?
2. Or x.
The final answer?
No, g of x. What would g of x be?
It's going to equal 1/3 x to the...
Okay, wait. The g of x. G of x would be x to the 1/3, right? And that's the first thing you do. Then you do 1/3 of 1 is 1/3 x to the negative 2/3. It'd be 1/3 minus 1, which is 1/3 minus 1. Again?
Negative 2/3.
Negative 2/3. Perfect. So that would be, so the first thing to do, write that in exponential notation, not in radical. X to 1/3. Then 1/3 times x would be 1/3 x to the minus 2/3. Subtract 1 from that, you get this. That moves it downstairs exactly like we had before, 1/3 x to the 2/3. We did that. Okay? Inadvertently. Oh, yeah. I think we're out of time, aren't we?
Just about. Okay, 1 minute.
1 minute? Okay, let's try one more. What would that be? Don't leave it in fractional form. What would that be? Y is equal to
X.
x to the second. What would it be? Yeah. Not that hard, folks. If it's in fractional form, move the x upstairs and negate the exponent. So that'd be x to the negative 2. No, not the derivative. The function. Y is equal to x to the minus 2. You see that? Move this upstairs and negate the exponent. So that's how you start. First thing, write it in exponential notation. The y would be dx to the minus 2. Now take the derivative of that.
Would it just be negative 2x to the negative 3?
To the negative 3. Negative 2x to the minus 3. The coefficient times the exponent, that's 1. Negative 2, and then drop the x by 1. That would be negative 2 minus 1 and negative 3. Then to write that back in fractional form, it would be a minus 2 over x cubed. Okay? Now I think our time isn't right.
Yeah.
So I think there may be one more. So we'll start with, where is it? No, that's it. All right. Well,
So there is a D.
what's that?
Wait, no, I'm looking at the wrong one. Just mine.
Yeah, that was top of page 112. That was the end of example 2. Now they
The next one.
continue with the power rule. And, okay, let's pick up there next time. Okay?
4 years.
That'll be our first slide next time. Have we done enough for any homework exercises here? I think probably so. I think you could do 5 if you wanted to, it has nothing to do with what we're doing now. But I know you could do 7, 9, 11, 13, and stop there. So 7 through 13. Odd 7 through 13. Good deal. We'll pick up the rest of those next time. All right. We'll see you then on Wednesday. All right. Look at this.
Okay, so right here, would this be, if I just plug this in, since this is 1, would it be 0?
Okay.
Or would I need to do more than that?
Okay. You need to do it on both sides.
Okay.
Approaching from the left or the right. Okay?
Okay.
And then that may be the right answer. I don't know. Okay. No, it's not multiple choice for me. So pick one of those. Okay.
Oh, yeah. Okay.
Yeah. And there's your paper. Excellent. Way to go. Oh, sure. Well, I don't know. Let's see. Yeah, I think I will give it to you. That's it. Well, if I can find it. I'm pretty sure I made enough copies. Oh, wait. I don't think she did make enough copies.
You had an extra student. You had someone new on that day, remember?
What's that?
You had an extra student. You had someone new on that day. First time showing up to class.
Oh, so,
Yeah, I do have one.
okay, thank you.
All right. Well, I may not have enough for the next person, but that's fine. I can make more copies. Okay. Yeah, you're right. I think we did have a new person in the class. All right.